Good afternoon. We are going to talk about today about malware detection. In the previous lecture, we looked at different types of malware and how they get installed and why it is difficult to find or detect them. And we briefly talked about some of the existing techniques. I am going to talk about few more techniques and zoom into this malware detection aspect. So, this lecture would be beneficial if you are trying to work in the malware detection area. So, here is a kind of a brief recap of what exists today. So, basically most of the solutions or at least the commercial solutions are software based solution. That basically means for all of those software based solutions, the key idea is the following. So, the key idea of the following for any of the solution any of the solution also known as antivirus, any of the antivirus solution that is installed in your computer, they basically scan your system on a regular basis if you keep the scan enabled, right. And the things that they scan, that depends on the basically the signature file. So, you have a signature file, you have a signature file in the system, and that signature file you can think of equation like x greater than or equal to 5, number of instruction less than something, and so on and so forth, and each of the entry corresponds to one malware. This could be malware 1, this could be malware 2, and this could be malware 3, and they have thousands of such entries they have. Now, you have to understand antivirus is also a software program. That software program is running, you have to keep it enabled, and that software program is running on your platform in your computer. So, this is your core 1 processor core 1, this is your core 2, right, and typically antivirus software in a normal system is supposed to run on the security enclave. If you remember the Intel SGX or TDX or AMD ACV, and we have a dedicated dev to talk about this trusted execution environment in the security enclave, or if the security enclave does not exist, then in the super user mode this antivirus software would be running here, and everything else, your normal application like your browser is running here, all other applications running here. The job of this antivirus software while running here to monitor what other programs are running in other cores, and while they are running, what is their footprint, what are they doing, and does any of them match with any of my signatures. So, that is why if you kind of if you use a Linux environment and in the command line you do a top, you are going to see a n number of processes running, and you might be wondering, wait a minute, only thing I did, and the one on the top would be top which you just started. You might be thinking I am not running all of them, many of them are system related, including the antivirus software which is running for monitoring all other software, which is checking the signature and then trying to figure out the program that is currently running, is it a malware or is it a benign program. Any questions? The problem with this idea is the developer of this malware is aware of this signature file. So, whichever company software you are using for, so let us say Symantec, or that is one of the most used one, or there are many other companies, whichever company software you are using is completely known to the attacker, what is their signature file, how many malware. In fact, this information is publicly available, signatures for different known malware. So, that is why in the malware community there is a concept of known knowns, known knowns, known unknowns, and unknown unknowns. So, known knowns is basically obvious, it is just you know. What do you think is known unknown? What does that mean about any malware? What do you think it may mean, known unknown?
It could mean that I know that there is something existing, but I don't know exactly what it is.
Could be, but in this case known unknown mean I know the malware, but the part that is unknown or I know the malware or malware type, let us say it is a botnet, but what I am unknown about how many of the botnets are attacking me. It is a denial of distributed denial of service attack, but how many of them are attacking I do not know that. So, it is a known adversary, but what you do not know. So, you have a friend, you know this person is going to stab you, but you just do not know how they are going to stab you. Unknown unknown is basically I do not know what software, what malware it is, and I do not know what it is going to do. And this is also known as 0-day malware. It is a new malware that just came in, that is also known as, let me write it out, 0-day malware. 0-day meaning that is the first day anybody ever heard about it. Of course, once it become known, semantic analyzes, semantic will find an entry for it, signature, and then they will do the update of your antivirus. In fact, it turned out I found out the hardest possible malware to fix would be when your antivirus software is getting installed or updating, you interrupt it. Then it did not finish itself, it will not kill itself, and it can't correct itself. Just try doing it, you have to throw that computer or you have to reinstall everything, and you can create that funny thing. But anyway, so the problem of this known unknown, known known, any of those, that this malware actually knows this stuff, whatever things you are checking they will change itself. That basically known as malware with obfuscation or metamorphic abilities. Obfuscation, as I explained, if the idea is a thief normally wears a jeans, then I do not want to wear a jeans, I will wear dhoti or pajama or whatever it is that is treated as a normal human being. So, then basically that would be like obfuscation. I am obfuscate myself as a gentleman, I obfuscate myself as somebody does not match with any of these signature. Metamorphic is because when I install myself in your computer, semantic will know about it, they will update it, I have to change myself while I am inside your system, I will change myself. So, while I am wearing a dhoti, I am also carrying a pajama in my backpack. The moment you put dhoti also in here, I will just change that and then I will start wearing pajama. If pajama also gets into that thing, I will need to pick out something from my backpack so that I can move forward. So, this is basically what I meant by can be bypassed by obfuscation or metamorphic features. So, then there are solutions people are talking about. I am going to zoom into one of these solutions with this whole lecture, so that you kind of see deep dive into how people work. So, hardware based solution, what is the key idea? So, what was the problem in this space anyway? The problem was, so one of the exact equation for a malware was percentage of branch predictions or branch misprediction. Let us say percentage of branch misprediction, that is one of the exact equation in the signature file. If as a developer of an or an attacker of a malware, if I know branches of misprediction, you are looking for less than equal to 0.2 or 20%, then I want to add a lot of branches in my code and I will let it mispredict, and those are fake branches, they have no effect to the functionality, because as a malware I want to do some functionality. Remember, ransomware tries to encrypt the code, those branches have no meaning, simply there are some branches if I greater than 5 and all that stuff, and you know that I will not be 5, and similar branches you can add, and the way processor deals with them, they start using it when it get mispredicted they will convert into no operation. So, that is where hardware based solutions become useful, because the instruction that getting killed as no operation, hardware knows about it. So, it is not going to count those branches that was mispredicted and was not never used. So, then it will only count the one that were used, right. So, that basically means if I take the example of human, we should be asking them to get rid of their clothes. That would be analogous to hardware based solution. We get to the rock bottom of the instruction that actually gets executed. The way we solve that is using something called, I mean there are many ways, I am going to talk about only 3 in today's lecture. One is hardware performance counter, second one is embedded trace buffer, and third one is electromagnetic emanation. These two are of course functional, and this is basically side channel. I intentionally chose those basically those 3, so that you kind of get an idea, and I want to tell you the whole big picture of the story of, and this story applies to any hardware based solution, and there are hundreds and hundreds of paper, although I cited one of my own, there are hundreds of paper in this area. So, the key idea is I want to have a malware detection mechanism installed in my computer, and as I told you, if you do not do it right, your malware detection mechanism itself would be one of the biggest malware if you ever encountered, if you do not do it right. So, malware detection mechanism is supposed to sit in your computer, and then it is supposed to continuously monitor what else is running in your computer device, whatever it is. And what needs to decide in layman terms, is it running any of the malware or is it running benign normal program? It needs to distinguish between normal and abnormal, right. And how does it do that? I basically tries to summarize by looking at all the papers that are out there. It is basically I need to look some of the hardware features. What features? Depending on, are you doing malware detection based on functionality, or are you doing based on side channel? So, depending on that you choose one of those. Then you need to choose basically different types of, what type of evasive malware, ransomware, botnet you are trying to detect, which one are you targeting. Third one is what solution you are using. For example, are you using explainable AI, are you using real time acceleration? Remember we talked about the GPU, TPU, FPGA based acceleration, what type of evasive attack you are accessing. So, that is basically the story. What is the end result? Either it says a malware detected and let me quarantine it, or it says it is a benign program. Of course, here I am saying as if you are running only one program, of course, you are running many programs. Any questions on this big flow, where this program sits and run to what is your final outcome, either it is malware or it is not a malware, and this is basically classification type machine learning in this particular example. So, let us talk about hardware performance counter based malware detection. So, first thing I want to talk about is that how many of you know about hardware performance counter? So, any processor you buy, anything in your computer, whether it is a ARM processor, whether it is an Intel processor, whether it is an AMD processor, MIPS processor, RISC-V processor, it does not matter what processor, even tiny microcontroller. So, like Motorola, Siemens and all those microcontroller in your devices, all of them comes with something called performance counter. What those counter counts? Different architectural events. So, I can list some of those events for you. So, for example, number of instructions executed. Now, you can control some of those based on the variables, number of instructions so far, total, number of instruction per millisecond, you can control that, but number of instruction. Then it would also give you, let us say, number of cache accesses, how many load instructions are sent to the cache, number or percentage of misses, how many cache misses are there, number of branches, how many branches are there, or what percentage of instructions are branches, how many of them are mispredicted. So, pretty much any architectural event you can think of, there is a counter for it. There is about 300 or 400 counter give and take, and most of this work when we talk about, people use normally top 10 or 15. The way you want to think about, now start putting the machine learning cap on your head. Each of these performance counter is nothing but a feature for machine learning tool. So, really machine learning very quickly need to figure out that out of these 300 features, which of them is more important, rank them out, top 5 or 10, and let us just focus on those, monitor those, build a model with those. When it builds a model, what it is really doing, you know, it is building that equation. Then you might be saying, wait a minute, if it is building that equation, number of instructions greater than this, something less than that, how is it different from what Symantec had on software based solution we talked about? Let me ask that question again. We have all these hardware performance counter, these are potential input for the machine learning model. Think of neural network. I am going to train the neural network based on those. I am going to tell them, by the way, this program you are running, this is malware, by the way, this is one you are running. So, then internally it is going to build an equation or a curve or a model that is basically going to say, well, if the number of instructions is greater than 1000 and percentage of misses less than something, it's kind of creates kind of a complex, it kind of creates a complex equations like that internally as a model during training time. Then during prediction time, if you run a program, it's basically going to match with that equation. If it matches, it's malware. If it doesn't match, it's a benign. My question is, it seems exactly the same. Symantec sends a set of equations to you, we call them signature, and machine learning model builds a signature. Then what is the difference? Why am I even trying to suggest, give a hypothesis, hardware based solution is more accurate? Why? What is the catch? Catch is the Symantec signature is static, malware signature is dynamic. You look at the behavior, look at the portfolio of the program, then you train and build. Now, you could argue, wait a minute, now malware knows that is how the machine learning model is built, it can do metamorphic changes, then you have to train again the machine learning model. Still it is a dynamic signature, you can change it, you can retrain it. But the key idea is hardware performance counter, as the name suggests, is counter, it counts. Machine learning model makes use of it, and I will show some of the usage. So, first thing we have to choose the input for the machine learning model, that is basically the counter, and I listed some of them, number of instruction, exception, change of context, bus access, and then thing is you have to train the machine learning model, use the overall statistics is vulnerable, sophisticated, and the most of the time people focus on this aspect of time sequential information. What does that mean? That means if you just use performance counter, let us say number of instruction, that is probably not going to help, or number percentage of misses. If you say percentage of misses between time A and time B, that difference if you look, that is more useful. That is the meaning of time sequential data. You have data at different time point, that is the sequential nature, that is the time sequential method. And if you want to do that, then recurrent neural network is going to be ideal fit for this kind of context, or you ignore all about this and you use large language model, then you do not have to know anything or learn anything.
Sir,
Yes, please.
last right now we talked about that.
Turn it on, please. Okay, I will repeat your question, you go ahead.
So, right now we talked that the signature gets copied by the attacker, and that is why they are able to metamorphose and other stuff. So, if the
No, signature is not copied by the attacker. Signature, we have to assume signature know, I mean attacker knows what signature is used, somehow they know,
so if
because rest of the world knows, everybody knows.
so if an ML builds that equation of some certain features or a combination of those, it is it not attacker won't be able to easily decrypt that equation from the ML and then like metamorphose just to get that change the signature.
So, the question is that it may be difficult for the attacker to know the equation inside machine learning model. Answer is yes and no. I think answer is yes from the perspective machine learning, if it is making a decision yes or no, it is not an explainable AI, nobody knows, forget about the attacker, nobody knows what the hell is going on. But the answer is no from the perspective that when you build any security objective or a lock, you can't assume, oh well, attacker or thief does not know the which day I am in my house and which day I am not. You have to assume attacker knows everything about it, still can you defend, that is the idea, right. So, even as close as 100 years ago, there used to be a dacoit called Devi Chaudharani, and she used to send letters to the houses that I am going to come on that day to steal your and rob your house, and she was successful every time. So, that is how, if you are an attacker, that is how you should be doing, and if you are a defender, you should be telling the rest of the world, this is how I am defending, I am pretty sure you will not be able to attack. That is the spirit in the security world. Everything should be known to everybody except the key. Now, moving target defense is one of the solution people use against metamorphic malware. It is very expensive. So, the idea is that I do not use one machine learning model, I use multiple. The way you as an attacker keep changing yourself, me as a defender, I will keep changing my classifier. How I do, what do I do? I use a random number generator. Then even if attacker knows you use a classifier, a single one, they might be able to do something. When they know I use multiple, if I am selecting them randomly, unless it is 2 or 3, it is almost impossible, theoretically impossible for the attacker to basically correctly predict which one you are using when. Assumption is the number of classifiers would be large enough, but the problem with this is practically you have to have that many trained model stored in your computer. It is going to slow down the detection, and as we discussed during ransomware detection, if it slows it down, then it basically by that time attack is over, game over. If I am dead, what will the bodyguard do? It is over, right. So, that is all, that is basically about hardware performance based. Next one I want to talk about the embedded trace buffer based. How many of you know what is embedded trace buffer? So, embedded trace buffer is one of the legitimate debugging technique in any design you have access to, not just processor, even network, router, anything. So, the key idea is when you have a design, there is a tiny buffer, although I am not drawing it that tiny, that would allow you to trace certain signals or variables for certain number of clock cycle. ARM allows you to do software control it, many architecture will not allow you to software control, like processors, that is hardware control, meaning during design time which signals would be traced for how many clock cycle. This is typically in the order of 128 signals, this is in the order of 1024 clock cycle. It is a very small number of signal, 128 out of millions or billions of signal would be traced and stored. There is a trade off, I will come to that in a moment. Yes, please. Do you have a phone there? No. Turn on the phone. Yes, now it is on. I can see the red light.
Sir, yes, in the previous slide you mentioned that we will be keep changing the seed, right? Each and every time the attacker knows that what I am using, right? So is it feasible, because the cost will be more and we will be spending more on the hardware part. So
right. So feasibility, that is a different problem.
Yeah.
Does that solve the problem? Yes. So as an academic exercise, publishing paper, it is perfectly fine. Whether any company will adopt it or implement it, that is a different story.
Okay.
So practically there are constraints as I talked about.
Yeah.
Right. So embedded trace buffer is basically a legitimate structure that is in the design. Most people do not know about it, they do not care about it, only people care about the people who want to debug after the design is fabricated. For you to understand, you have to think about this. If you have million line of code you have written, right. Now, debugging million line of code is a problem. All of you want to go to industry, make money, you do not want to do PhD with any of us, that is all right. But the thing you will quickly realize as soon as you go, you are cleaning somebody else's piece of shit, not documented properly, it is all hacked code, bunch of morons wrote it, and if you want to modify the code, your boss will say go and become a professor. We do not do that, do whatever we asked you to do. Millions of lines of code written by people, nobody knows, they left the company and you have to fix it or fix bunch of bugs within certain day, depending on the severity of that bug. Now, yet if you want all those millions of variable, you can do printf. I know printf and it running for millions of clock cycle, that data would be in terabytes, you will not be able to dump or load. Now, think of hardware, any integrated, tiny integrated circuit has billions of transistors and you do not have any printf facility. Anything goes wrong, your boss says go and find and fix it, hardware can't be fixed. That is why firmware patching is done, as I talked in the first day. So, what do? Do you ask for blessings from God? That is not going to solve the problem, I can assure you, that is not going to solve the problem. That is why one basically intermediate solution is allowing little bit of space, this is very tiny space, 128 or 256 multiplied by 1024 bits, allowing that, but then there is a lot of associated problem I will not talk about. Is it which 128, which 256, that is not going to give you 100% visibility, but which of the signals if you trace you get maximum visibility. If you think of an AND gate, if you trace the output and output at that point happens to be 1, you know these two dude and you can continue that stuff, but if this output is 0, you do not know what are the inputs, right. But either way, that is the key idea and there is lot of research, how do you select trace signal whatever, but for this discussion what is relevant is that is known as embedded trace buffer, a tiny buffer that is only solely used for debug purposes. Now, remember this debug is not necessarily during design time, this debug could be during design time, mostly during deployment. Anything goes wrong, then customer says oh my god this happened, that happened, you do not want to spread Disney magic wand, you want to just stop the execution, dump the trace data and from that try to make sense out of it and pray and all that stuff you do, that is the embedded trace buffer. Now, how do embedded trace buffer we are going to use? So, that data also you can use for your malware detection. Lot of people talk about using cache data, register data, but the problem of that is how quickly the malware detection software can download that registered data. The amount of time it takes to download the cache or registered data, that might be long enough for attack to be successful by then. Any questions on what is embedded trace buffer? It is a tiny debug infrastructure that is useful for debugging. Think of in lieu of printf, that is all you have in an integrated circuit that is already fabricated, right. There are also concept called scan chain in the design, I did not talk about here, but scan chain basically all the sequential element you have, remember any design is sequential element and combinational logic, all the sequential element you have they are scanned connected in a chain, of course sequential logic connect. So, this is kind of a multiplexer here. So, scan chain idea came from the point of view, again that structure got inserted by different set of people, manufacturing testing people. The reason they inserted, when they want to test a chip for manufacturing defect and they need to pump values to these flip flops to initialize to a known state, and if you have millions of flip flops, initializing that to a known state will take forever, not a minute, not hour, it will take days to even do one valid testing, because you cannot test a device without initializing it to a known state. You can't wake me up and ask me interesting question, I am like who, what, where, when. So, I need to be initialized and reset. So, that idea scan chain was invented, so that you keep pumping data whatever values, it goes through a chain. If you have a million flip flop, then you know it will take million clock cycle, that is a lot, but that is still guaranteed. If you do not do that, if you want something to pump and then you the sequential logic combinational logic computes, it produces something and then depth of 5, 10, 20 or 100, that is going to take forever, non-deterministic amount of time to initialize the all the flip flop. Lot of attacker makes use of this scan chain also, but this time we are only talking about how as a defender you want to use it. How do they take advantage of scan chain? Anybody can tell me? We talked on the day of assertion based validation. So, in the scan mode, when you are doing scan, the time this is used and time this is used, they are totally different. This is typically used after it is manufactured. Let us say chip is manufactured, you built a robot, that robot is used in the Amazon facility to kind of carry the stuff to the truck or wherever, and something went wrong. People would stop that robot, download this data and test. This is used when an integrated circuit that got manufactured even before putting onto the robot, that integrated circuit, are there any manufacturing defects, such as let us say you are drawing two lines, did one of the line, it was supposed to go like this parallel, did it touch one another, this is called bridging fault. Or maybe you are drawing a line, did it got kind of disconnected. Remember, these are all nanometer level. So, here in the order of millimeter, micron would be 1000 times smaller, nano would be another 1000 times smaller, million times thinner than a hair, million times thinner than a hair. That is what those lines are. Some of them might have been disconnected. How do I test it? I put a 1 here and I see if I get a 1 here. To do that, I have to initialize the whole all these flip flops, then I put a 1 and then I check for 1. So, wire by wire, for each of those millions of wire I have to test. Unless you are going to a company to do manufacturing testing, you will never learn about it, but attackers know about it. You as a defender need to know. How do they do attack? So, this is used during only manufacturing testing time. How would attacker make use of it? Normal execution going on. Remember, in normal execution, the key which is used for encryption and decryption will travel through the system, and there would be a point when key would be completely out in the open right here, which is right in the scan chain. That 128 bit key or 256 bit key would be right in the scan chain. If an attacker can stop execution right then and there and change to manufacturing mode, change the setting of the chip to manufacturing mode, they will be able to dump it from that scan chain.
So, it's like a leakage test.
It is not a leakage, it is basically, can you detect when that computation is going? That is a legitimate time when that value is supposed to be there, because key is used for encryption and decryption. If encryption is going on, key should be there. You can't say, oh, I am hiding the key, I will not. If you have a door with a lock, you have to take out the key to open the lock. If your thief is standing right behind you, when you open the lock, thief will get in the house with you, that you can't control. So, that is why in around 2010, 2015, the idea was, the solution was, well, once this manufacturing testing is done and the chip is placed on the robot, this would be sealed. So, that we will not be able to have a mechanism to push anything in from the scan chain and push anything out. Then people found a problem with that. Then so a lot of solutions are in between, but these are the structure that can be used for malware detection. So, let me now get into, instead of zooming in, let me kind of zoom out and talk about how do I go about it. Previously, I talked about hardware performance counter, that gives a global perspective, how many instructions. Embedded trace buffer or even scan chain gives you local perspective, right. So, analogy would be, let us say you are looking for the best PhD student or your best spouse possible in the world, and somebody gave you a feedback, yeah, he or she was in my village, kind of a good student. That is a global perspective. Local perspective is you go to that school or where he or she studies or teaches and you see for a day. Of course, that is one day story, that is one snapshot, one picture. So, one picture versus a movie which is a picture running in every 20 millisecond frame. So, hardware performance counter gives you an average or a statistics about an event, about a person. This one gives a snapshot of a 1 day, 1 minute, 1 second, whichever you look at it. If you can combine them right, then malware detection would be ideal. So, that is basically what it tries to do, and machine learning model makes use of it. And trace buffer, this is what I talked about, this is the full story. When you design something, of course you verify, but after you manufacture and all that, you have scan chain, which I did not show it here. You also have a trace buffer, and during debug you need, actually not necessarily during deployment, even before you do the deployment, when you want to put the processor, operating system, compiled code, and you are trying to test it, we call it post silicon validation. At that time also this trace buffer is extremely useful. So, when you run machine learning model, then the first thing you want to talk about, how is it doing in terms of different parameters, right. You are trying to choose different kind of stuff. So, here I am showing you different exploration experiment. So, true positive and false positive, as the name suggests, if during detection it detected a so positive in this example would be benign program. If it detected somebody as benign, it is truly benign, or it is detected somebody as benign, it is actually a malware, it made a mistake. And this diagram is showing, if you increase the ETB width, embedded trace buffer width, basically more signals you are tracing per clock cycle, then your true positive goes up, and of course naturally your false positive will go down. That is one issue, that is expected. If you have more data, more information, if you have too much more, then machine learning would have another problem, overfitting problem. One more thing it also establishes, we looked at different neural network. First day I talked about normal neural network, I talked about decision tree, I did not talk about random forest. Think of a lot of decision tree together, which is a forest, lot of trees in a forest, lot of decision trees together solving a problem. And if you are trying to figure out which one we choose, it turned out that which one is this normal neural network is actually not that great, but all others are kind of hand to hand, and I am still trying to figure out this brown one or red one. So, this neural network, that KNN, that is basically kind of tends to be doing a little better than rest of them. So, basically that is how you kind of decide which neural network model to use, you decide how much of data, what size of design I can use, sometimes you do not have a choice. This particular one makes assumption you have a control of telling the processor designer what size of ETB, embedded trace buffer they should put in. Most of the time you do not have that choice, you have to stay with whatever design it came with. Yes, please.
Sir, when we talking about
The switch is not on. Yes, please. Oh, it still become off. Maybe keep it on, hold it, it will become red.
Sir, when we're talking about the problems with machine learning models, there is either false positive or false negative. There are two categories of problems. One is like intrusion detection or malware detection, where false negative is very serious than false positive. Suppose we are detecting a suspicious user in a system, and if our system show it is false negative, that means it can lead to a large data breach for any organization. And if it is identified as true false positive, then it will be go for further investigation, even it is a normal access. But false negative is here serious issue. And when we go with the other category of problems like behavior analysis, where false positive is more serious. Suppose a system shows that this kind of person have serious psychological problems, even it has not. So how explainable AI can help us to address the these two categories of problem where we have need false negative address mainly, and some other category of problem where we have to address mainly false positives.
Right. So, first short answer is explainable AI cannot help in the exact question you asked. So, false negative is of course dangerous because a malware you allowed it to continue, but when you talk about false positive, even that is not that great, it is not that serious, because if a program is executing some health monitoring system or something and you kind of identify it as a malware, system will shut it off. Think about it, you are running experiments for last 10 days and your paper submission deadline is tomorrow. So, and system shuts it off as a malware, I do not think you will be happy. It may not be as serious as somebody encrypting and asking you for money, ransomware, that attack. So, for killing a legitimate program thinking it is a malware is not a great idea either. Now, going back to explainable AI inherently has the ability to give you some internal information. What you want to do with it, that is kind of different, and I will have some example on the microarchitectural attack days to show you how explainability can help you reduce this false positive, false negative, but it still reduces that by allowing you to train it better by knowing what is going on, not by any magical the nature of explainability. Yes, please.
So, you mentioned that the scan chain or the trace buffer is not accessible during functional mode, right? So, in the sense when it is installed,
when computation is in progress.
So, then how this kind of AI technique will work? The scan chain you want to be able to access, right?
Right. So, yeah, very interesting observation. So, the question is, if you have this scan chain or trace, so first of all, trace buffer you could be able to use, but scan chain was kind of not allowed during normal execution. Then the question is, if scan chain is not allowed during normal execution and if program is running, how would your malware detector make use of any of the scan chain data? So, again remember, malware detection is working in the super user mode. So, as a super user you might have certain privileges to do certain things. For a normal outsider we should not be allowed, and one of the way malware work, they elevates themselves to the super user mode and then they get access to some of these data. So, there are those examples, but in this particular case when the malware detection we are doing or all the academic exercises, they are basically stopping the execution, dumping the trace buffer and analyzing them and saying if we could have detected it instead of in lifetime. In fact, for hardware performance counter also same argument applies. Hardware performance counters are nothing but some functions. If you call them too many times, you are interrupting the speed of normal execution of other functions. And hardware performance counter you also have to access in super user mode. You cannot just access, you cannot just get in the command line and ask for tell me how many instructions, you cannot do that. So because of that it introduces overhead. So that is why even when you do any research you probably have to instrument your code with hardware performance, basic block, all that. It is going to significantly slow down the execution of your malware detection algorithm, and if that slowdown is too much, that is not a good solution.
So, in general, how do you access the trace buffer when I have no idea?
So in general trace buffer is dumped through the debug port in general. Now the question is, once you kind of in ARM processor for example, this is not like hard coded like this, which is all the signals are hard coded completely wired to this and only connection is through the debug port. So internally you can choose which variable you want to trace and internally registers can read and write through that. So in that kind of software controlled trace buffer you will be able to download those values.
It's something that when I run my program,
you can run your program.
I told that you only track my XYZ variable, right? So then they will map those XYZ variable to those registers.
Some of the input ports of this trace buffer, and then you will overwrite after every 1024 clock cycle. So you will be able to software programmable trace buffers you will be able to control. Hardware programmable you have to dump, you have to stop execution and that kind of stuff. So that's not like real time malware detection.
So modern processor may not be supporting that, but earlier days they used to have just JTAG cable. So small board they provide JTAG cable for doing programming and to debug the code.
So this is the JTAG port, the one is coming out, this is called JTAG port. So you will be able to dump the data
But
through
nowadays
that.
modern system they don't provide this thing, but earlier days they used to provide.
So many of the modern system disabled it for security reasons, but they still provide. JTAG is a international standard.
Yeah.
They have to provide some mechanism. Otherwise, anybody can buy anybody processor build system. Then there would be no way of chaining them together. Like bus specification, JTAG also interface port. So now, of course, if you do just HPC hardware performance counter or ETB, the kind of false positive it kind of creates depending on which architecture, it basically ETB tends to do well in most of the cases, false positive are less. Now I want to move from functional malware detection or machine learning algorithm using functional values as input, whether ETB, HPC, to electromagnetic side channel. So there are days when is it tomorrow? So Dr. Karfa will talk about side channel, but today I just want to give little bit of start just to connect the dot for malware detection. So the electromagnetic emanation, let me talk about what is EM stands for, electromagnetic emanation. So this is a electrical property. Of course, we did not talk about power side channel attack, and in layman terms, if you are computing certain functionality and if your device is connected to the power supply, and if I can kind of connect my ammeter or whatever to the power supply where you are drawing power, if I know how much power you are drawing, from that I can figure out what you are computing. That is the basic idea of power side channel attack. And electromagnetic emanation also relies on the same principle. It is just that when there is an electrical activity going on, whether it is consuming power or dissipating power, it dissipates these creates that magnetic field, as the name suggests, electromagnetic field. And if you have a probe you are holding, this is a probe. Typically probes look, if you are holding a manual probe, it will have a handle and then there is a loop around it. That loop will be able to detect. But today, these days, if you are buying high end probes, those probes are very microscopic probe and they move in every millimeter across the surface and they collect the electromagnetic emanation. So capturing electromagnetic emanation itself is an art, because even you are trying to, on an FPGA you are trying to capture, the problem is FPGA where those tower are, or tower microscopic towers are, you have to hold your, first of all you have to know where your logic is and which power supply in that FPGA. If the power supply is here, then for this particular block or set of blocks, you have to hold the probe right here. If you hold anywhere else, you are not going to get the footprint, that one. Then you have to understand there are other stuff going on for controlling FPGA, controlling communication, other stuff going on. They will also contribute to this probe, that noise. So that noise is very significant. So unlike power side channel analysis, which is very robust, if I can know how much power you are drawing, electromagnetic emanation is lot more difficult to get reason, because if you do not do it right, what you are going to see, bunch of noises, even when you are computing, even when not computing, noise is so much more than the actual computation. Everything will look like a band of, let me, this oscilloscope they are not showing, everything will look like a band of, so this is the band that you are seeing, everything will look like a band of ups and downs, there is no clear demarcation. That is why there is a notion of amplification, hiding noise, subtraction, differential power analysis and all that, but that is the idea of electromagnetic emanation. Now this is also widely used for malware detection, it is very successful. So people are able to show that using electromagnetic emanation you can identify how many for loops are there in the program, and if you know the program, which for loop started now. So that you can do almost 99.99% accuracy. You can figure out what is going on right now using without touching, and the good idea of EM is it is non-intrusive. For power supply based attack, either you have to allow me to connect to your power supply, or your device should have some kind of transistor, you should allow me to embed in your design, so that I can measure the power consumption across that one. That is intrusive. Why would you as a normal user allow me to insert a transistor in your printed circuit board or in your computer for me to do these measurements, but whatever it is, that is still intrusive, and you sometimes it may not be applicable, but EM you can always apply, but EM has its own downside. So, if you are starting side channel kind of analysis research, you want to start EM at the end, you want to start with power based side channel analysis, and then you probably want to do delay based side channel analysis. Once you are successful, then you probably want to go for EM based side channel analysis. But whatever you do, because of the availability of EM signal, then EM would go to like oscilloscope, you get that, then you feed it to wherever you want to feed it, then it goes to machine learning model, then machine learning will figure out whether a malware running or not. And how does it figure out? It is the same philosophy. The philosophy of if you recall that in the power side channel analysis, when we talk about, by looking at these waveforms, we can say, well, this is where add operation is going on, this is no operation is going on, and this is where let us say multiplication or square root is going on, because we kind of know how much each of those instruction computes. And in fact, many cases we will be able to figure out because some of the cryptographic day I will talk it more, elliptic curve cryptography, which is one of the most powerful cryptographic algorithm before this post quantum cryptography came in. It has a silly computation inside. If the ith bit of the key is 1, then do something, else do something. This loop has more instruction than this loop. If somebody is observing power variation and you are seeing it goes up, then little, then it goes up and then little, then you know this one is 1, this one is 0, this one is 1, this one is 1, this is 0, you exactly figure out what the key is. But the thing is, you have to identify in that whole story of the oscilloscope where that key processing started. Once you identify those boundaries exactly, then you can exactly find out what is the key through kind of power side channel attack. Same thing you can do through EM. EM is like kind of less reliable. You have to do lot more processing, you have to run lot more traces, you have to do lot of trial and error and elimination, much harder, but you are going to get to the same thing. So, since I am talking about this, anybody knows what is the solution for this? What is the solution people use today? It is called masking. Only reason I am able to figure this out, because this is imbalance. If statement has more instruction, else statement has less instruction. I will put bunch of garbage instruction just to match with this one, so that the power profile becomes exactly the same. But the problem of that is you are unnecessarily introducing power consumption. Instead of going power efficient solution, you are going power inefficient solution, right. So, that is basically EM based malware detection. Now, there are a lot of research effort, and I do not believe some of them are published, some ideas that you could publish as a paper, that can we combine hardware performance counter and EM based solution. How do you do? I have 2-3 ideas I just jotted down. So, hardware performance computer kind of do well with certain things. If certain things is benign, then it is likely to hold. If certain things seems malicious, it needs deeper inspection, and remember this gives a global view, and like embedded trace buffer, EM gives a local view, more detailed view. Think about it, zoomed in. So, this one is giving you a lot of trace. Out of the trace, HPC is zoomed you into the tiny part of the trace. Now, you zoom into that trace to the EM based detection, then that is saying it is benign or it is malicious. So, for when you have programs with interrupt, story works slightly differently. Certain programs has a lot of interrupts, then HPC will be able to do normal execution, and or if there is an interrupt, you do interrupt handling, and then on a normal execution you can do EM based detection. Some other thing, if it is a ETB traces can aid EM based detection. So, for example, there are control intensive programs, then you can start with EM based detection, and if it is a control operation, then you go with embedded. If it is a data centric operation, then it is a ETB. What is control centric? If you have too many for loops, too many if statements. What is data intensive? Think about all the multimedia code and GPU, lot of data processing, not too many control flow. Then this kind of method would be a better combination of EM and HPC. Some people have tried other different ways depending on the thing, depending on what access you have. So, for example, so there is a whole day dedicated for network on chip. So, this is what one of the network I am showing, or on chip network, where you are kind of have some network where the traffic is going on. The only sad part is the traffic inside the network is essentially unencrypted, because doing encryption and at that speed and that lightweight is kind of a problem. But whatever it is, if the attacker or defender is able to download that data or whatever is going on, then you can mount kind of different type of attack or different type of defense. And many time, if any of you have access to any of the new AMD machines, you might be able to download this. For many others, there is no direct access to any of the network on chip network, any of the dumping ability. Now, the way, if you want to evaluate any of those, if you want to start experiment, one of the board that kind of going to work for you is Zinc SoC evaluation board, and this is one of the most popular board. One of the reason that is the case, because this board pretty much has everything you need, different types of port, and you have the FPGA in there, you have the processor in there, you pretty much have everything in there. So, you can program them, and this particular one, the k nearest neighbor and all that, some of the experiments you have already seen, and these experiments I am going to show you, PN scan, bash light, Mirai, those experiment, and in the benign benchmark netstat and ping. One of the reason these benign benchmarks we chose, because these are also used by PN scan for sure, some of them bash light and Mirai also. So, when ping or netstat runs by themselves versus they are called by some malware program, can you differentiate them? That is basically the complexity. And again I am showing some data on HPC and ETB, the actual data does not matter, who does better. If you have access to network on chip, depending on the so this percentage is basically injection rate, what rate of injection your data is, then there is a different kind of portfolio between false positive and false negative story. Now, for all of these malware, this slide I have shown earlier, for all of these ETB based or hardware performance counter based malware detection, some of the models people used, I showed it earlier, I want to zoom in. So, data format that typically is useful is basically, I call it register, sometimes getting register values are difficult. It could be some ETB values, it could be hardware performance counter values. So, wherever may be, these are the sources and these are the clock cycle, certain values, whatever those values are, that is the data that you need to provide to the machine learning during training, that is the input. Then typically, because it is a time sequential data, typically recurrent neural network, and specifically there is a name for it, long short term memory, LSTM, that is actually perfect fit for this kind of malware detection data, and most of the paper use some variation of recurrent neural network and long short term memory. I have seen most of the papers they use long short term memory LSTM model, and this particular for malware detection case, people is more successful using gradient descent to kind of quickly converge on a decision that whether it is a malware or whether it is a benign. You can use other ones, and if you can show better than the existing papers, then that could be a good paper by itself. And this particular one I talked about. So, once you have all these information from explainability AI perspective, the way it helps, you get certain values associated to certain clock signal or certain variable, then whichever has the highest weight, then you kind of know that so think of this one as the weight of that polynomial. So, that weight is higher, that basically means something happened in clock cycle 4. So, here is some kind of some results to show you the detection accuracy of bash-light malware using different kind of random forest, decision tree and all that different kind of models. And in this particular example, explainable AI models are doing better. Of course, the whole story I am not talking about that how much iterations it took and how much effort it needed for explainable AI versus others, and you would expect the similar analogy for PN scan and as well as the Mirai example. One other thing that is also important, we talked briefly, it is not just the accuracy, can you detect the malware, are you detecting some of the benign program as malware, that is the false positive rate. That is why anytime you do research or publish anything, in addition to showing those three diagram analyzing, you have to present how many of the cases you are catching it as a wrong answer. So, you are catching a benign program as a, and you want to make sure your solution is better and in terms of false positive rate than the state of the art or whatever you are comparing with. I believe that brings me to the conclusion. So, malware is a serious threat to computing system, and we talked about different software based solution like antivirus software AVS, and they can be bypassed. I basically talked about how do you use some of the hardware primitives like hardware performance counter, trace buffer to kind of solve those problems, and I kind of show certain types of result where it could help you in good malware detection. So, if you have any question, I will be happy to take, otherwise have a wonderful day.